And the first speaker is Bijay Kumar, and he's going to tell us about photonic and electronic properties in quantum dot circuit-QED systems. So could you go ahead?
All right. Thank you. So thank you for the kind introduction. And I would first like to thank the organizers for the invitation. Uh, so today I'm going to talk about some work that we did in the direction of the circuit QED systems. So I'll mainly focus on photonic and electronic properties in a particular type of circuit QED, which we say CQED system based on quantum dots. So this set of work primarily was done in collaboration with Manas from ICTS, Divira from Toronto, and Shaul Mukamil in Irvine. But I'll be mainly focusing on this reference, the first reference, and this is the model that I'm going to talk about. So I'll come to that later, but let me just first talk about the outline of this talk. So I'll first try to motivate you why the CQED type of systems are interesting. Uh, and then I'll move to this particular type of quantum dot CQED setup. And I'll tell you how we sort of look at or how we compute various type of properties and what we learn from these systems. In particular, this type of devices from the practical aspects one tries to realize a photon amplifier or a laser. So in this region, quantum dot region, these are essentially a maser, and we'd like to understand how you can get those behavior out of these small systems. And then we'll see what one can say about large scale circuit QED setup, and then I'll try to summarize my talk. So what is this CQED or circuit quantum electrodynamics? So this is essentially nothing but you have some kind of a quantum circuit which is out of equilibrium, and this circuit can be made out of, let's say, even a simple quantum dot, which, let's say, in contact with two baths, which are at different chemical potential that drives current through the system. So this is a what we call a circuit, and you basically place this circuit inside a cavity. And that essentially mimics a cavity photon. So what you have is essentially a very, sort of a small scale system where you have a purely quantum system where you have a light matter interaction. So this is essentially an excellent test bed, this type of setup, which can answer fundamental questions related to light matter interaction, where the matter can be is basically the quantum circuit, which has a lot of controllability, as well as these kind of systems can also gives you many practical advantages. So there are many experiments in recent years that are happening in this direction. So if you want to know more about it, these are in the bottom, there are these two review articles, latest review articles in this direction. So what are the things that you can do with this? Well, first, these are kind of systems which are widely tunable. So you can actually tune many parameters in this kind of setup, and that gives you access to various new parameter regimes that were often not accessible in various other experimental platforms. And this also challenge to theoreticians that whether can we sort of explain those sort of experimental outcome by bringing advanced level theoretical tools, if not those are available. Uh, then the other interesting fact is that you can actually design different type of circuits. So here I'm showing a picture about a single quantum dot. You can have multiple quantum dots and various other type of fabrication that one can do, which also leads to many interesting properties. So this is also a kind of scalable kind of property that this kind of quantum circuits or setup offers. As well as when we talk about this circuit, we have these dots coupled to baths. Now, these baths could be also very different. They could be normal leads or metallic leads. They could be superconducting. They could be ferromagnetic. So, in a sense, this type of setups actually gives rise to what we call engineered quantum systems. So, you essentially have this kind of setup, but you could actually play with your circuit. You can change the leads. You can drive the systems, and you can actually engineer various type of interesting Hamiltonian and look at various type of interesting photonic as well as electronic properties. So it comes with various tunabilities, and this is what the quantum circuit QED is what means. And what we are interested is trying to understand some type of some physics from that gives rise, that basically comes out from this type of setup. Okay, so in terms of measurements, real measurements, experimentally, what people can measure. So so in this slide, most of the figures are taken from this particular paper from Science in 2015, where the experiment was done in the double quantum dot setup. So I'll come to that later. But in terms of measurement, what experimentalists can measure is essentially the photon transmission. I'll tell you more about it, which essentially captures information is that how much gain do you have, or how much amplification that happened in this device in terms of photon. You also can measure emission spectrum, the photon emission spectrum, as well as you can measure the statistics of photons. So whether so what kind of, so when the photons are coming out, what basically their statistics is. So all these kind of measurements can be done, and that comes with very high tunability that this setup offers. So this kind of setup has created a lot of buzz, and you can see here again, this is this particular 2015 papers, where out of this double quantum dot, the Peters lab in Princeton was able to realize a maser out of it. So these are interesting things, and what we are going to do is to basically try to understand one particular setup, which is essentially consisting of. Now, let me tell you in some detail here the setup, which is nothing but you have double quantum dot. I will tell you why we don't consider single quantum dot. We'll come to that later. But let's just for the moment take a double quantum dot setup, where you have there's a parameter called epsilon, which we call the detuning, and this TC is nothing but the tunneling between these two dots. And now, in order to drive these dots out of equilibrium, what you do is to put two baths in contact with two dots and keep them at different bias that basically drives current through the system. And so this is your non-equilibrium circuit. And what you now do is to place this whole thing inside a cavity, and basically that gives rise to a light matter interaction. And the question that you ask is that, can I have this electronic circuit as a gain medium to generate photons? Okay, and if these photons that are coming out, what is the gain? Do I even realize a maser and things like that? So all those things we basically try to understand from this sort of a simple setup. And these are in the table, what you see as the various parameters in this problem. This is it's mainly taken from these two papers by Peter's group. And you can clearly see that very nice separability in terms of these parameters. You see the light matter coupling is in the range of megahertz, whereas the electronic regime is in the range of gigahertz. So this will actually help us to build up the theoretical insight. So this is the setup that I'm going to primarily focus on, the double quantum dot or DQD setup. But before I move into that, let me just tell you that there is a variant of this model that exists in a slightly different way in the community of quantum transport. So here is what I've been talking about, this double quantum dot with coupled to a photonic mode or a cavity mode. And here, if you're a quantum optics person, you are mostly interested in looking at the photonic properties. I mean, that is the main part. But on the other hand, if you go to a quantum transport person, he will look at this device and he will probably interpret this photon as a primary phonon mode. And there is a lot of study that people do to understand electron transport in presence of vibrational degrees of freedom, which we call phonons. And so there is a lot of interest in the quantum transport community to essentially understand electron transport there, where people not only look at how the transport on an average electron is flowing. People also look at, for example, higher order statistics. And so essentially people do thermodynamics, and there is very nice sort of universality that people observe in this kind of non-equilibrium system, something known as universal fluctuation relations. People talk about what about various type of impurities. You can have a harmonic oscillator like a phonon, that when electrons are flowing interacting with an oscillator, which is a infinite level system, or let's say you have a couple of impurities which are like two level systems, how do you see the signature of that in the electron transport, as well as you can realize various type of engines, like for example thermoelectric engine or diode effect or heating or cooling effect in this kind of setup. However, same questions you can as well ask here, but often if we come from, if we look at these systems from the quantum optics perspective, we often just look at the mostly the photonic properties. But there is a simply a one-to-one connection in that sense, because this phonon here, you are interpreting these as phonons, but these are essentially, from a theoretical aspect, they are essentially very similar. Okay, so now let me come to the actual setup and give you so we are going to actually deal this problem completely microscopic manner. So we are going to write down all components of this setup, the entire Hamiltonian of the setup. So let us quickly look at that. So the Hamiltonian consists of the matter parts. When I say matter, that's basically the electronic part, the light, the cavity part, and the cavity matter or light matter interaction. Now matter is slightly complicated. It has various components. You have double quantum dot, you have the leads, as well as you can have these quantum dots are can interact with phonons. So it's a very general model in that sense. So the matter part is essentially a double quantum dot, so you can realize a charge qubit. So I should mention that we are sitting in a Coulomb blockade limit, meaning at any instant you can only have one electron in the dot. So therefore, you can realize finally a charge qubit, and you can write in a very simple form. Now, the parameters that we should focus is this epsilon, which is nothing but the detuning between these two dots, and Tc is the tunneling, the coherent tunneling between the dots. You have a standard coupling between these dots and the leads. The leads are fermionic. These are the lead Hamiltonian. And this is the coupling between the dot and the lead, which essentially telling you that there is a probability of electron pumped in to this left, and probability of electron going out, and the Hermitian conjugate as well. So these are basically pumping the electron into the dot. And you have a standard double quantum dot phonon coupling. So when electron is residing in the dots, they can interact with phonon, exchange energy. So that's the matter part. So that's slightly complicated. The cavity part has a single mode of cavity photon with frequency omega c. That is also an important parameter. You have the input and output ports, which essentially you can model it as baths as well. You can also call them transmission line. And there is a coupling of this cavity mode with the transmission line that essentially gives you the mechanism of decaying, the decay of the photon, which we often call this kappa L and kappa R. And finally, the most important is the light matter interaction, which is given by this, where this A is of course the cavity operator, the cavity mode operator, and tau Z is the matter operator. Okay, and
So,
G is an important parameter, is the light matter coupling.
so
Okay,
excuse me, can I ask a question? So
sure. Right.
let me just make sure. So in the Coulomb blockade regime, you never have more than one electron in
That's
the
true. That's true.
double dot. Is that right?
That's true.
Okay, thank
Yes.
you.
So you basically have three possible states: zero
Mhm.
electron, one electron in the left, or one electron at the right. That,
I see. Okay,
yes. Yeah.
yeah, thank you.
So finally, given this Hamiltonian, what you can do is that since you are interested in the cavity and the double quantum dot, what you can write is a master equation involving these two degrees of freedom, the photon and the double quantum dot, an effective master equation, which is essentially given by the Lindblad master equation that you can write, which has a unitary part, and this unitary part has a time dependence, and I'll come to that. But otherwise, this H0 involves the cavity and the double quantum dot without the leads. So you basically trace out all the other degrees of freedom that you are not interested. And that essentially gives rise to these three different dissipators or Liouvilleans or Lindblad non-Hermitian parts essentially in the master equation. So this can be very simply achieved. It's not very complicated. So now the reason of making this Hamiltonian time dependent is that if you are interested in doing a transmission measurement, then what you have to do is to supply an input field and look at the output field. So this is essentially in very short, this is essentially the input field that you are basically applying to your cavity. So this is a coherent driving term, and that's what makes this Hamiltonian time dependent. So this omega d is the driving frequency. That's another important parameter. Okay, so one caution that when you write this Lindblad equation, what we should do is essentially write in the global basis, in a sense that we should diagonalize this Hamiltonian and then write this Lindblad equation. So when you diagonalize, you essentially get, because of this rotation, it's like you're rotating, which gives you, it's a 2 by 2 rotation. It gives you this cosine theta and sine theta that are related to this epsilon, which is the detuning, and Tc is the coherent tunneling. So you get these parameters floating here. So the sine theta, cosine theta will floating around. Omega is basically now the gap between these two levels. So that is important. So you write your Lindblad in after diagonalizing your system Hamiltonian, and accordingly you correctly take into account all these corrections because of this rotation that you did to diagonalize it. So that's just a side statement, but it's very, very important. So your light matter interaction now get a g sine theta, and remember this theta is coming because of the rotation. All right, so this is the Lindblad equation with the dissipators coming from the electron, the photon, and the phonon, and these are not very difficult to see what these terms are. So very quickly, the electronic term is coming because of the electronic baths, and what the baths are doing, they're doing nothing but populating and depopulating these two levels, right? So these are various rates with which you can either populate the ground or excited state, as well as you can depopulate, and the various rates are getting controlled by this coupling strength, the gamma. Remember, the gamma is the coupling strength between the system and the bath, the electronic bath, and these theta components are basically again coming because of the diagonalization. So that's the electronic bath. It's just it's just giving you the populating and depopulating rates of electrons. The photon bath essentially gives you the rate at which photons decay, photons leak from the bath. If you're in the low temperature, this is what you get. If you have finite temperature, so this is like the spontaneous term. If you have the finite temperature, you will have more terms to it, but let's just focus on the low temperature limit. And for the phonon bath also, the kind of interaction we have taken, it gives rise to the phonon can as well induce transition. Remember, the double quantum dot simultaneously interacting with the fermionic lead as well as phonon bath. So phonon bath can also induce transitions. So there are various rates that you will basically get, which will depend on the coupling as well as the phonon bath temperature. So this is basically, there is an upward rate, meaning it can pump the electron from ground to excited state, as well as de-excited, or you could they probably don't do anything but rather than exchanging energy. Okay, so these are various terms in your master equation coming as the dissipator, because you traced out the bath. Now, once you have this reduced master equation written in the Lindblad form, you can very simply write down the equation of motion for the quantities that you are interested in, so essentially you can write the collective set of equation of motion. Now, remember, when I'm looking at the cavity, I also have this driving term because we am doing the transmission measurement, and this is the set of equation that you get. But while writing this, we have made a very important approximation, which is known as the semi-classical approximation, that whenever you come with this kind of expectation, you basically separate them out. So certainly this is not true always, but at least you can intuitively sort of agree that this can happen when the light matter coupling is weak, because this is the matter part, this D is matter part, A is the cavity part. You're separating them out. So roughly speaking, this can happen in the weak light matter coupling limit. So if you have that, you can solve this problem. You can solve for the transmission. So what we are looking at is what is the transmission in this, and this is what you get out of this equation. Okay, so the transmission now very interestingly has this particular form. Now what this form essentially tells you is the following, that this transmission, so you're looking at the cavity transmission, it gives you information about the matter, and that matter information comes as a charge susceptibility. So that is one of the, so it's basically nothing but the density correlation in some sense. Okay, so this is the charge susceptibility, which is entirely is a function of the matter part. So if you control this, then you have a lot of controllability in the transmission. and the transmission essentially gives you an idea of the gain in the photon. So if you look at this little carefully, it depends on various parameters of the electronic medium. For example, the bias voltage, the temperature of the leads, the various couplings between the double quantum dot and the fermionic leads as well as the phononic leads. Now, another thing that you immediately realize is that there is this kappa, which is the decay rate, and this chi double prime is the imaginary part of the susceptibility. So this gives you a threshold condition that this has to be, so this you can trust as long as kappa is greater than equal to the imaginary part of this. If it is less than that, if this becomes negative, you cannot have this equation to be trusted because your solution for A will diverge exponentially. So you get a threshold condition, which is this, that you can figure out from here. Now, we actually did an took alternate approach to actually get to this expression, but that was for a slightly different model, which was this same double quantum dot setup, but without phonon or without Coulomb blockade regime. We incorporate this scale-dish non-equilibrium Green's function approach, which essentially tells you that the transmission is nothing but the response function of the cavity. And that's what we call the DR. And if you look at the response function, you exactly get, even from this Green's function approach, the same looking form. And this response function is nothing but is essentially the a retarded Green's function of the cavity operator. And once again, this is the same.
Excuse me, Bijay. This transmission, is it computed in the linear response regime or?
Yes, yes. So this is the assuming that the field is small. So so the transmission is essentially you look at the response in the linear order of E. Yes.
Okay. Okay. Thank you.
Okay, so you get the transmission, and you can immediately figure out that this response, this charge susceptibility, this correction is nothing but the charge susceptibility, which is the non-equilibrium charge susceptibility. And that's what appears. And since it's a response function which follow the causality principle, there is a strict sum rule that you can prove that the integral of this transmission over all frequency is related to kappa. So that's a sum rule that you get out of it. So I'm not going to get into the details, but this is a very formally is a very nice approach where you can actually write down a Dyson equation for this response function or this Green's function, the cavity Green's function, and you can see how this charge susceptibility term. So essentially, your cavity is seeing the density response. Okay, so that's that, and how this essentially appears. Okay, so let me now show you what this transmission tells us. So you see the transmission is essentially tell you the following, that if I don't have light matter coupling, which is G equal to 0, my transmission is perfectly unity at the cavity frequency. All right. Whereas if I now turn on the light matter coupling, but let's say my bias is 0, my electronic bars are at 0 bias, what happens is that I see transmission drops and it gets broadened. The reason is that your chi double prime is basically negative. So your electronic media is yet not a gain medium. It's actually a lossy medium. So your photon is essentially seeing two dissipative medium. One is the cavity itself, the cavity ports, as well as the electronic medium. But the moment you make the electronic baths away from equilibrium, you make the chemical potential finite, what you can have is a possibility of population inversion. And because of that, chi double prime can become positive and it can compete with kappa. Okay, so it can become smaller and smaller. So the broadening reduces and you can have gain. Now, gain is what? If the transmission goes above 1. And that is what you precisely. So by driving the system out of equilibrium, you have a possibility that electron flowing from one end to the other and releasing photon. That is basically the principle. And it's entirely getting controlled by this charge susceptibility. And you very simply, you can again figure out this, that if you see the transmission as a function of delta mu, it's always less than 1 when it's a finite, when it's a 0 bias, and in fact, when the bias is less than the cavity frequency. So you need to, in order to generate cavity photon, you have to at least supply that amount of energy. So when you cross that, your transmission goes above 1, and that precisely gets reflected by the imaginary component of charge susceptibility here as well. If you now vary as a function of epsilon, which is the detuning, you actually see this peak and dip structure, which is often observed in experiment. And this is very easy to understand. If you have a positive detuning, so when electron is going from left to right, it actually emits a photon, and that's essentially gain in the transmission. Whereas the dip is essentially negative detuning. So here the electron transport is getting assisted by absorbing a photon, and that's getting reflected by a dip, and corresponding signature you can as well see in the phase. And if you look at the contour plot as an epsilon1 and epsilon2, so that's like the two energies of the dots. So then you can very easily see these peak and dip structural lines as a contour plot. And you can as well look at as a function of epsilon and driving frequency that where the transmission is having a maximum peak. So this is the place where you have a maximum gain. So all this tunability essentially can gives rise to various interesting physics. Now let me move to another interesting part. So far what we did is a semi-classical limit of this whole problem. We got a threshold condition beyond which we cannot trust the result. And more than that, what we were interested is to learn about the statistics of the photons that are coming out from the cavity. So then what you have to do, you have to essentially write down a population equation for the photon, for the cavity mode. And this again you can do following the quantum master equation, where if you look at this, I'm not going to get into the details, but if you look at this is basically the cavity decay part, which is pretty standard. But this part is what essentially gives you the terms involving light matter interactions. Okay, so this G and E are telling you about the matter part. Now, this is a kind of a difficult equation to solve or close, but you can do it in a particular limit, which is very nice. And this is essentially what we call the Scully-Lumb approach. So here is one approximation that you do. It's called the adiabatic limit. And what is this limit? This essentially tells you that, okay, let me assume that the time scale that is in the electronic degrees of freedom are way faster than the cavity time scale. So essentially, let's assume that the non-equilibrium steady state for the quantum circuit they obtain the steady state much faster. So you essentially solve for the steady state for the double quantum dot and substitute that solution here. And that helps you to close this equation, and you get a very non-trivial type equation in terms of this very complicated actually expressions given in terms of these coefficients A, B, and C. So I'm not going to show you those expressions, but try to give you some meaning of that. So if you see, the A always comes with, A is a term which you can actually relate to gain, and AB is a term related to loss. And how do I understand? So if you look at A pictorially, this is what it means. So A, if you look at the expression, it tries to tell you the following. It's proportional to the rates of populating the excited state and simultaneously depopulating the ground state. So if you think carefully this particular process, then this is actually able to give you a gain, right? Because you're populating excited and depopulating the ground state. That can only happen by emitting a photon. So this is what this term A, if you look at closely, that is what giving you. AB is basically you reverse the arrows. So AB is a process where you populating the ground state and simultaneously depopulating the excited state, that you can only do by absorbing a photon. So that you don't want if you want to realize a photon amplifier. So that's kind of a loss. Okay, so then that is how they come into this picture. And C is a term which essentially depends on the light matter coupling as well. So this is a central equation for the dynamics, and it's a closed one, but it's non-trivial. But you can actually solve this equation for any value of A, B, and C. But let us look at this below threshold. So when I say below threshold, what I mean is that, let's say light matter coupling is weak. So this is a regime which we so far actually covered. So if it is small, then what you can actually show is that you can ignore this denominator. And then you can very easily solve, and you can actually show it's effectively a thermal distribution. So below threshold, what you have is that the photons that are coming out of the cavity is essentially distributed thermally with some effective temperature given by this, and this is the population distribution. Okay. And most importantly, what you realize again here, that this threshold. So remember, when I'm talking about this distribution, I should have this guy A by AB plus kappa to be less than 1. If it is greater than 1, your solution diverges, doesn't make sense. So your threshold condition is essentially this. Okay. So what is this? As from the previous picture, A is the gain, AB is the loss, and kappa is the loss. So you have a computation between the total gain and total loss. So if if gain is greater than the loss, that's your above threshold. If it is less than the loss, is below threshold. So this is the threshold condition we get from following this Scully-Lumb approach. What you can actually show, and what we have shown that this precisely matches with your semi-classical result. It exactly matches. This threshold condition is absolutely the same from this approach and from the transmission approach that we did earlier. Okay, so that is an important message. So now you have these two crossover, you essentially, so you have this below threshold is a thermal distribution, and above threshold what you have is essentially a Poisson looking distribution where you essentially have a large number of photons, and this is like acting like a maser. And the most important point is that this threshold limit, you can actually, because it depends on the charge susceptibility, or in other words, depends on the complete the parameters of electronic degrees of freedom, you have a large tunability and you can actually control these threshold limits. So for example, if you reduce kappa, you very easily cross the threshold. If you can increase the G, the light matter coupling, you can
Vijay?
also, yeah.
Ask a quick question.
Yes, Prasad,
So
right.
here above threshold, it seems like there is, of course, some kind of lacing or macing. But do you think there is a way to get also some kind of phase locking? Because in some sense here the phase
Phase is
is
arbitrary, right?
arbitrary.
Yeah. So
Is it something that you can get if you keep going to higher photon numbers, or is it some finite size effect, or it's not
I
possible?
cannot comment. So phase is arbitrary. You are absolutely right. So I'm not sure whether that behavior of phase logging will be observed. I'm
Okay,
not
fine.
sure.
Yeah.
Yeah. So what I was saying is that this varying these parameters, you can actually cross the threshold. And here you see, for example, if you tune electronic parameters, so these are very easy to control. Your delta mu or your epsilon, which is detuning, these are very easy to tune, and you can actually very easily cross from one pattern to another pattern. Okay, so very quickly, I think I have near about like 5 minutes max. So I'll just flash a couple of more results. So far we looked at just the photonic properties, but you can understand the light matter coupling. What is the effect of light matter coupling in the electron transport? So you can as well ask that, and that is also experimentally measurable. So a very general formula that you can actually start looking at is basically the so-called Mayer-Wingen formula that gives you a way to investigate current. So in the lowest order of light matter coupling, so here is a weak light matter coupling that I'm focusing at this point. You can actually have these two diagrams, which are essentially given by the Huttry and the Fock diagram, and that if you feed in and you look at the current, you very nicely see the effect of this light matter coupling in this plot. So if you look at the blue is essentially without the light matter coupling. Okay, so that's G equal to 0. But if you turn on the light matter coupling, at least to the lowest order, what you see is that this asymmetry in your current, and this is essentially telling you that there is this inelastic process going on, or in other words, there is a photon assisted transport, and that's the signature that you see in your current as a function of epsilon. Okay, so far this was all about double quantum dot, looking at the photonic and a bit of electronic properties, and how you can essentially cross this threshold regime if you want to realize a maser. There are now efforts also to sort of scale up this kind of systems. So there are various ways to scale up this system. So one way that I think was done, it was done in this 2015 science paper, where in Jason Prater's group, where they essentially took a double quantum dot but two copies of it. Okay, so you have two copies, but here I have drawn it for multiple copies. So you have multiple copies of double quantum dot, and you put that in a full cavity, and then you explore and ask what happens to your transmission. So this is actually a very simple exercise, and you can actually show that as long as light matter coupling is weak, all these copies of double quantum dot actually adds additively. Okay, so all you have is that you get a response which is n times, where n is the number of double quantum dots, n times the charge susceptibility. Okay, so in other words, you now have a very easy way to reach to the threshold. Okay, and that makes sense because you have enlarged your gain medium, and that now you can see if you have the look at the transmission for n equal to 1, 2, 3, 4, as you keep on increasing, you are getting close to kappa, you are able to fight the cavity dissipation, and you can realize more and more gain. And you also see the reduction of the the increase in the amplitude and the reduction in the width. And that's something that, if you remember the sum rule that I mentioned, that the area under the curve is constant in a sense. So if you reduce, if you increase the peak, you have to have the reduction in the width. So that's something that one can explain from there. So here is a plot in the log scale, which you see that as you keep on increasing the number of double quantum dot, you have a way higher and higher gain in the photon, because you have enlarged your gain medium. And the other way that you can actually have scale up your quantum circuit, circuit is basically having multiple sites sandwiched in a within the leads. So this is another setup that you can have, which is very similar like a cascade model. And here also you can actually ask the question that what happens to the gain. So interestingly, of course, you won't get a gain if you just have a single dot sandwich between two fermionic leads. The reason of not having any gain here is because you don't have any resonance condition. If you have at least you need two quantum dot to satisfy a resonant condition, right? So certainly for single dot you won't have a gain, so you at least need a double quantum dot, which is m equal to 2, and you see a gain. And then it actually has some non-monotonic behavior in terms of gain, but at least you can scale up, and you can scale up in terms of gain by increasing this medium. So I think I'm very much done with the talk. So let me just quickly summarize. So this kind of quantum dot circuit QED setup can serve as excellent quantum devices. You can realize the amplifier or even as a maser, as well as from a fundamental side also we can try to understand about the light matter interaction. We have sort of given out the principle for gain, which is essentially that you have these various sources of dissipation. The major dissipation is the cavity decay rate, and now you have to fight that dissipation by bringing the gain medium, so which is basically giving you the charge density response, and you have to increase that in order to get a gain. And this particular threshold condition, that is that decides whether you have a thermal distribution or a Poisson distribution. So that threshold condition, you can actually have a lot of tunability in terms of your matter degree of freedom or electronic degree of freedom. So with that, I would like to thank you for your attention, and happy to take questions if there are any.
Okay, so thank you very much, Bijay, for the excellent talk. And
thank you.
Are there any questions? So please feel free to unmute yourself and ask questions, or you can just use the chat box.
Hello, Bijay. This is related to something what Prasanna already asked. Your formalism only captures the diagonal component of the photon statistics, right?
Very true. Very true.
Is it possible to push it to like compute this phase locking effects and all that, like compute average amplitude averages?
So you mean the phase locking? It's yeah. So can you repeat again? Sorry, Hari.
If you can compute like things like average A and it turns out to be non-zero, can we expect something of that
Oh
sort?
no, I'm not sure. So let's see. So average A, no, right? Because you only are dealing with the population equation, right?
That is after adiabatic elimination.
That is
Right?
after adiabatic elimination. True. Here at this level, I'm not sure. I mean, it's a super complicated equation that whether you can close it. Yeah. So we had to make this approximation to proceed further. One has to again come back to this and see if something what you are saying is absolutely right. That we are just looking at the population. One has to go beyond in order to really understand. If you don't make this approximation, yes. But no, I can't comment on that. I don't have an answer. Sorry.
Can I have one more question?
Sure.
So, Bijay, when you are talking about transmission of this scaled up system, you had some sort of collective coupling of this different circuits to the same cavity, right?
That's right. Absolutely. So
in some context, yeah.
So the entire thing is coupled to a single cavity mode. And that's why you see a collective effect, which is n times. So the cavity essentially see this whole n copies. And because it's a weak coupling between the cavity and the matter, it just adds up. It's like the cavity seeing this as a bath, and you have, the bath effect of the bath is like the additive if you have n baths.
So this looks pretty similar to the super radiant situation. Typically, in those cases, emissions should scale like n square, right?
Yeah, but this is not n square. I mean, yeah, I mean, this is not super radiance. This is a very simple effect. Like, if you think from even like a master equation, if you have a system, if you have two baths which are weakly coupled, the effect of the two baths are essentially additive. So this
So,
is, yeah.
so the like feedback renormalization of
No,
this
no, no, no,
circuits is not accounted for.
no, no, absolutely not. That
Okay,
completely
so
misses.
that might capture the n square difference.
Exactly. So this is actually something that is a question that me and Manas have talked about, and we have not really gone in that direction yet. But yeah, but that's a very good point.
Okay, thank you, thank you.
Also, maybe I wanted to add that even in the n copies, like each copy has its own source and drain bias.
That's
So,
all.
so that is also important. So each copy has its own source and drain bias. So it's each copy is itself a gain medium.
Its copy itself is a gain medium, and we have taken it to be identical so that you can essentially write n times this. Otherwise, we will have a summation of coming from each gain medium, right? Precisely, Manas. Thanks for pointing that out. Yes.
Okay, so any other questions? So if not, so the time is almost up. So let's thank Bijay again.